Today is the second session of our Lunch and Learn on DFC Software. The first one was the 23rd of May, where we did a very high overview of the technology and everything on how DFC incorporates MSc Nastran, MSc Apex, and Patran to ultimately automate the stress analysis of aerostructures in particular, but ultimately anything else as well. So I'm not going to put my camera off instead of screen. I'm not going to do a lot of talking today. By the way, if you guys want to see the first session the first session that we did in the 23rd of May, you can scan the QR code. The session was recorded and it's available on our YouTube page. The second session today, I'm not going to do too much talking. I'm going to leave the deep dive content for JJ. I'll do a quick recap of what we did in the previous session, but I want to get to the stress methods and the analysis involved when we use DFC software in the whole process of certification for aero analysis. So a quick one, like I said, I'm not going to go through all the details that we did on the previous session, but ultimately we've discussed the conventional workflow of doing stress analysis and how we can ultimately use DFC to streamline these activities and to make it more efficient and to ultimately automate it. I'm not going to go through the details of it. Like I say, you're more than welcome to watch this session or the first session of it. But yeah, ultimately, we want to get to a stage where we have FEA models and we can use a single button to create the events and the scenarios, create the BDFs that's being solved in Nastran, to create the calc files, calculate the calc files, create RF maps, and do that all in a standardized, structured method. So that's the dream that we are heading towards, and we'll cover a little bit of that or go into the detail of that today as well with regards to the calc files or the methods associated to particular to aerospace stress analysis. So again, the details, DFC stands within the center of the three major products within the MSc1 licensing system. We use Apex to build the models. We use Nastran to solve those FEA models, and we use Patran and a little bit of Apex to ultimately create the RF maps. And we also and DFC stands in the center of that in managing that workflow for you, but it also does the load extractions to ultimately compare that to standard stress analysis methods. Like I say, the details of this is all in the previous session. I don't want to go into the details of that, but just a quick refresher or a recap. We ultimately want to get to a calculation where we compare an allowable load that's been given to us by some of the standard stress methods that's out there today, and we want to compare that to applied load or that's being extracted from a finite element model. So like I say, today we're going to focus a little bit more on the methods that's included in DFC software. There are several of them. I've included a few examples that you see on screen. I'll get to the ones that we're going to discuss today, and that's the ones that JJ will also go a bit in more detail in. But ultimately, what I need you to understand is that we use the FEM models to calculate those loads, and those loads are being compared to any method that's included in Bruin, in the NACA methods, in NUI or NIWI, however you want to pronounce that. And what you see on screen is obviously not all of it. There are several more that's included in DFC. And what's also important to recognize is that DFC is also customizable in the fact that you can bring your own methods, your own validated experimental data or analysis data that you can use within DFC software to ultimately automate that as well and to produce standardized stress documents and reports for certification or for your own traceability activities. So for today, we've identified two methods, one being stiffened panels, which is a very, very common aerostructural design component we see in the aerospace industry, as well as fasteners. The stiffened panels is something we see a lot in aerostructures, and something like joints is something that's, well, there's very much of those, and if you can automate tasks like that, I think a lot of time is being saved for the analysis of big structures. So JJ, if you don't mind, can I hand over to you for the deep dive of these two particular methods?
Yeah, Zach, no problem. Let's just share my screen.
Excuse me. I couldn't join the meeting before because the link that's in the calendar doesn't work. A colleague of mine sent me the new link, but I didn't get the update. So you might want to send the meeting link again to all participants from before. I think that's why we don't have that many people. I don't think people are able to attend the meeting right now.
Thank you. I will do so. We are recording the session, so we will share that with the contact list again. Thanks a lot, Aman.
Thanks.
So Zoxo, carry on, or are you quickly going to send out those links again?
I will do it in parallel, JJ, but like I say, since we are recording this, you can continue. And then, yeah, I'll do this in parallel as well.
Okay. Let me start. All right, so this topic is just want to showcase DFC's fast and discrete joint analysis capabilities, and then after this is the continuous joints, and then the stiffened panels. So what is a joint? So a joint is basically anything, everywhere we use a fastener to join things together in an aircraft. So there are thousands of these things in the aircraft. Each joint allowable is different due to geometry, the material that's used, the fastener that's used, etc. So the value added by DFC is to manage this process in a sorted, standardized and automated way. And as always, the aim of DFC is to minimize the calculation errors, to save time, and to reduce the cost of the analysis. Right, so this with those roughly about 15 minutes, so we're going to quickly show how do we do fasteners, discrete joints, and continuous joints. So if we look at a fastener or discrete joint analysis method, so that's basically the RF calculation. So on top of the line is the allowable load, the load line is the applied load, and that ratio gives you the RF. So the allowables we get from material data as in Brun or something like the ARM PDS, material data sheets or whatever testing that you've done. So that will give us the allowable loads in terms of a tensile load or shear load for fastener, and included in that is the bearing allowable. If you want to include the joining parts to the calculation. So that's where we get allowables from. In terms of applied loads, we then get that from load extraction from Nastran results. So we solve the FAIR model with Nastran, and then we extract those loads with Patran. And that allows us then the combined thing to calculate an RF. So how do we do it in DFC? So we assign the discrete or fastener data to connectors in Apex. The connectors supported in this process are rigid links, flexible links, and bushings. And we use those connector loads. We extract those connector loads to get the applied shear and tensile loads. And then obviously we calculate the RF by comparing that to allowables that we get from our other calculation or test data or from other sources. And DFC comes with let's call it an estimation tool that you can calculate these allowables with, or estimate the allowables with. Right, so if we look at our fastener RF calculation, so this is using a standard interaction equation where it's use the stress ratios of the applied shear load and applied tensile loads. That gives us a stress ratio, and then we use interaction constants applied to that interaction equation to actually calculate the RF by solving this equation, as shown here at the bottom. That will give us the RF for the fastener. In terms of the other things, so the shear strength, we apply a shear correction factor as per the ARM MPDS, typically driven by your diameter of the fastener and the thickness of the joints. So typically, when joints contains sheets that are thin, normally that reduces your shear allowable for your fastener. So we take all of that into account. Bearing allowables are calculated either by the simple formula of your bearing strength times diameter times thickness. For protruding head fasteners and typically for countersink fasteners, you use the test data as typically in ARM MPDS to get the combined bearing and shear allowable for that joint. And then the bearing allowable is then just simply the allowable bearing over the applied bearing. So very simple calculations. We also include a prying load estimation. So notice if you model joints without contact, the prying load introduces an additional tensile load on the fastener. So the way we estimate that is we extract the bending moment from the connector, and then using a prying factor, we just divide the bending moment by that prying factor, and then we can add that load to the fastener to get the resultant tensile load. So this is a way of estimating tensile loads, additional tensile loads due to pry at the joint. So let's do a quick demo of how we do it with DFC and Apex. I'm just going to show the resource database with allowables. How do we import the data and assign it to connectors in Apex? And how do we extract it? And then how do we add those data to a DFC calculation file? Starting. Right, so here we have a simple test model. We've got a couple of connectors, flexible links, bushings, and rigid links. So we want to assign some data to it. So the first step is we need to open DFC, our DFC project, which we previously created. We now connect DFC to Apex. So that means that DFC and Apex are connected and we can interact with Apex directly. Then we have in our analysis data fasteners tab, we have already some fasteners there, but let's just add a fastener. So we open up our resource database that contains, which is a database that comes with DFC with all nice goodies for fasteners. We've got all the typical fasteners in there. Then we also have our joint estimation tool that you can use to estimate allowables. You absolutely don't have to use this. You can just use your own allowables. You've got your own test data. And then to import the data, you just simply select the data you want to import, which I've... Right, so I haven't opened the database via DFC. So let me just do that. Okay, there we go. So now DFC is connected with Excel. So now we can import data. So we just select any fastener there and we simply import it. Right, so now you can populate your project with whatever fastener you're going to use for that project, and you have the allowables for it. Then to assign it to things in DFC, you select your allowable that you want, or your fastener you want to assign. Then you select your connectors in Apex, either in a model tree, or you can use the mesh pick filter that's provided with DFC. And you select them, and you assign to connector. And what we do now is we actually rename that connector to add the design data to it, so we know what to do with it once we extract the data. So let's look how we can extract the data from Apex. That's my next step. Right, so let's go back to Apex. So now we simply use our auto extract selected CAE data tool. In the menu, you put your connector pick filter on, you select all your connectors that you want to extract. Then we automatically extract all the data. And if you view the log file, we then show all the data that's been extracted required for the analysis. Going back to DFC, we go to our data CAE data import. Then we select what we want to import. So we want to do a fastener analysis and a discrete joint analysis. We check the boxes and press execute, and we import that data. So I've already imported previously, so it warns me that there's duplicates, so it won't import it again. So all the data, all analysis are now populated in the database. We've got our discrete joints. It's all grouped by the element type per joint ID. We've assigned our extraction method, how we want to do it, and we have our extraction entity, other elements or nodes. And typically for rigid links, we want to extract that in a coordinate system to align the shear and tensile axis with the fastener allowable. So for each calculation set, you also have the functionality to actually then visualize what is applicable to the calculation set in Apex. But then we highlight the particular connectors for those calculation sets in Apex, so you can see what you're working with. In terms of fasteners, we can do the same. So that's a fastener and RF calc. And again, we can look here at where's our fasteners applicable to that calculation set. So now in the workflow, you can go to where we solve. So we solve Nastran and eventually attach and extract all the results, and we extract all the loads for each calculation set. So next step is then we could create our calc file and populate our method with all the input data. So I've done that previously. So let's just have a look at it. So the calc file is then basically the beginning of the stress dossier with the method data populated automatically by DFC. All the joint data point to the load file data. You can add fitting factors, etc., to the method. And then it contains the load file data for each of the joints that we've specified. And that points to the load file with all the data in it, load data in it, which we then analyze. Let's close all these things. All right, so then the next step is we just then press calculate, and it will then calculate the RFs for you. All right, so that's how DFC to discrete joints and fasteners. So let's have a look at continuous joints.
Can I quickly interrupt you, JJ?
Yeah.
In that calc file you showed, there will also be then a RF summary and a just the explanation of the loads involved.
Yes, that's correct.
Okay.
All right, so continuous joints. So how we do that is We assign, again, like we did with fastness, we assign joint data to Apex, and for that we use beam spans as the identifier for a continuous joint. So what we then do is then we extract for the applied loads, we extract the 2D elements connected to that beam element. And to extract the applied running loads for across the joint. So elements on the opposite sides of the joints are grouped in pairs to enable applied load calculation. Right, so, and then various joints can be specified. So you can have continuous joints, single joints, overlap, or one-sided joints. So that all influence the way that we calculate the applied load to the joint. So that's how we get the applied things. And then obviously our allowables, and then again comes from our joint data, either calculated or tested. So we use discrete joints. You analyze your allowable using the discrete joint allowable tool, and then we just simply divide it by the pitch to get the allowable running load for that joint. Again, this tool is available in DFC. It comes with DFC, the resource database. So let's just have a look quickly on how we do it in DFC. How we use dummy beam spans, how do we extract it? Looking at the element pair extraction, 2D versus 1D stiffness extraction, etc. Let's quickly go here. Right, so as I explained, we use beam spans to identify joints. So there we've got a meshed span, and there we've got two beam spans that are not meshed because the stiffness is actually modeled in 2D. So we just use dummy beam spans, which we do not mesh, to assign the joint data to. That will then allow us to do a continuous joint analysis there. Right, so again, the extraction is just done simply by selecting all the edges. The edges will then identify the beam spans. And then we can simply then import the data. And here we check then our continuous joint analysis that we want. Again, I've already done that, so it won't duplicate the entries. So let's have a look, focusing on the element pair extraction, just to show the concept there. So what we do is we extract, let's go to my elements. So we extract the elements at skin A and skin B, both sides of the joint. And they are paired as per entries in the list. So the first entry in the first list is paired with the first entry in the second list, and so forth. So 8380 and 8326, those are the first entries. So if we highlight our extraction of the elements and we just probe the IDs, and you'll see that those elements are paired. So at that region of the FEM, the loads locally there will be then used to calculate the applied load for that joint. And then it will just move on to all the other element pairs like that. In terms of 1D versus 2D extractions, so there we had mesh, the beam element were, the stiffness were meshed with 1D elements. This is what we can do with 2D elements. Even if they are connectors, you can still do the continuous joint. And this is what we do when there's, for instance, a 2D stiffener that's glued to the skin. So there's our glue elements. What we do is we ignore those glue elements and we do not include them in the calculation. So we pair the elements across the glue to each other, so we're able to do the joint calculation. We also make sure that we extract per joints. So we only group the elements as defined by the beam span that defines the joints. So we only extract, so those are paired together for that specific joint, for that specific allowable in that region. So in terms of the applied loads, so we want to align the applied loads with our analysis system. So we extract the loads in a coordinate system so that we are able to align the loads in the direction that we want them to be. In this case, it looks like I've selected the wrong coordinate system there. So let's quickly just fix it. So here we use the old pattern way of using the projected vector of that coordinate system. and we extract the loads of the shell elements projected to the x-axis of that coordinate system. So that will then sort out the load directions that they're all consistent with the analysis. Okay, so that is then how we do discrete joint, continuous joints. And again, all methods and calculation processes with references are documented, and that's available to DFC users to scrutinize and agree or not agree with. If you don't agree with it, we can tailor it to your requirements. Or if you have already done some coded way of doing it, then we can accommodate that as well, so that you can benefit from the automation benefits from DFC, but using your own methodology to calculate the RFs. Okay, so that is discrete joints and continuous joints.
Can we quickly just gauge with the audience if there's any short questions or that we need to cover, or do we need to do it afterwards?
I think for time, let's just go through it, and then we do all the questions afterwards.
Okay, sure.
I propose that we just do that. Okay. Right. It's different panels. Right, so let's have a look at our stiffened panel analysis capability. Zak did quickly show how we do it in DFC in the previous lunch and learn session, but let's just go a little bit deeper in it for now. So what is a stiffened panel? So that's typically an image of what a fuselage structure looks like. And everywhere we have a stringer attached to the skin between frames, that's defined as a stiffened panel. And there are hundreds of these in an aircraft, which we need to analyze. The tricky thing here is that each stiffened panel allowable is different due to geometry, materials, joint configuration, the stress state in the stiffened panel, and the allowable calculation is a complex, time-consuming iterative process. So again, with DFC, what we try to do then is to standardize and automate this whole process with proven methodologies, again, with the aim of minimizing calculation errors, save time, and reduce your cost of the analysis. Right, so what we're going to quickly have a look at is the capabilities of DFC. So we can do stiffened panel buckling to estimate the initial buckling of the panel. Then we can also do the post buckling of the panel. We can accommodate both 1D and 2D stiffeners, whether the stiffener is either 1D or meshed in 2D. Can accommodate both flat and curved skins. And the failure modes, we consider both compression and shear failure modes, skin buckling, stiffened panel, column buckling. We do flexural, torsional, and the interaction of those two. Look at force crippling failures, skin shear failure, the joint failures, as well as inter-rivet buckling. So let's again look at our RF formulation. So our allowable data we then get from our proven methods like the NACAS and the Bruns, etc. We get our allowables for force crippling, shear allowables, diagonal tension factors, etc. So that's where we get all our allowable data and method data from. And then in the applied part, we do load extraction from master results with Patran for the skins, and for 1D stiffness, we also do load extraction. Where the stiffness is modeled in 2D, we actually do a stress extraction from the master results to enable us to calculate the applied load. Okay. So in terms of the method, again here, what we do here, we use beam spans as the identifier for a stiffened panel. So we assign a joint allowable to it, and then automatically DFC will then also recognize as a stiffened panel. when you do the CAE extraction using the custom tool in Apex, we extract all the skin data and geometry like materials, thicknesses, panel widths and lengths, etc. And we do the same for the stiffening member or the stringer. We get all the material data and geometry from the auto extraction. Now to calculate applied loads, so that is basically then our effective stiffener, which is the combination of our stringer and our skins on both sides. For the skins, we only use half the width of the skin, and that creates an effective stiffener. Then we calculate the applied loads on the stringer and the two skins, and we sum them together, and that is our applied loads to our effective stiffener. So in terms of our stringer loads, that we just use the elemental loads from the beam elements, or we calculate it using the stress data from 2D stiffness. We've got the area, we've got the stress, and that then we can calculate the load. In terms of the skins, we export the fluxes, and then we use the load flux in X multiplied by half the width to get the applied load in the skins. And then for the shear stresses, we use the shear flux in the skin divided by the thickness to get the applied shear stress. So this is how we then calculate the applied loads for the stiffened panel. Then in terms of getting our allowable loads, if we just look at the effective stiffener buckling and force crippling failure. So in terms of our column buckling data or whatever, to get the effective section properties. So in compression, at the instance of buckling, we have a uniform stress distribution, and post buckling, those loads are then focused where we have still stable cross sections located at the stringer locations. And then according to the methods as per the NACA and the grooves, then we use an effective width to calculate the section properties of the stiffening member based on the compressive stress that's applied to that effective stiffener. In terms of our shear loads, at the instance of buckling, we just have a constant shear load in our skins, and as the load increases, that additional shear loads are reacted by diagonal tension loads in the skin, and that creates a compressive load again on our stiffness, which you need to take into account. And the same as for the compressive part, we also use an effective width of associated with this stringer, which is also linked to what we call a diagonal tension factor in the skin. So the more buckled the skin is, the smaller the effective area becomes. Then to get the allowable, so we use those effective areas, and that's in an iterative way to actually calculate the column buckling allowables. As you increase the load, your section properties change. So these things are interrelated, and you need to go through an iterative process to actually converge to a point where these allowables converge. So there's an iterative process to get it for our compressive part and also for our shear part, our shear compressive part. And then we get allowables in compression and shear. And then we then simply this is just to show that we have methods to do that in a quite efficient way. It's a very time-consuming process, but using the coded methods, I mean, that's 6 seconds, that's 4 seconds, that's very quick. And to calculate your allowables, all the effective widths and diagonal tension angles, etc., etc. So that's all taken into account. And then we use the standard interaction equations to calc the combined buckling RF or the combined failure RF for the effective stiffener. So that is then just do the global buckling and failure RFs. So if we're looking at our skins, joints and interrobot buckling, So again, there's a method in the NACA and the Bruins that we can calculate the combined stress state to analyze for skin shear failure, joint failure, interleaved buckling. So that basically means that you calculate adjusted buckling allowables. So these will, due to the combined compression and shear, so basically these allowables are lower, so you have a higher state of applied stress, smaller section properties, etc. And then you can calculate the combined stress state based on the combined loads. And then we can use our method to calculate. Oh, I've got a doggy that's barking there. Just hold on. My apologies. Okay, so we were yeah, so then we have a combined stress state, and with that we can calculate RS for skin shear failure. We can get our running load requirements in shear and in tension. I've just shown the shear one here, and then we also can get the combined stress to calculate our interleaved buckling RF. Right, so let's do a demo quickly again on how we do this. Can we use a dummy beam span to identify, or a real beam span to identify different panel data, how we extract it, and just quickly show again the images, element pairs, and how we do 1D versus 2D extractions. Again, we use our little previous model. So again, we use beam spans to identify different panels. There we've got, again, our 2D beam span. And that one we specifically want to use to calculate data, because that stiffness is actually changing in section across the beam span. So we assign 2 beam spans here to accommodate that. Again, we extract the edge data to identify the different panels. We import that into DFC, so I've already done that. So you also have the option then to capture images, and that just to show you the calculated set, where each calculation set is used in the analysis in the FEM. So you have a nice reference for it. Just coming back again to the element pairs. So again, we extract the loads on both sides of the joint. Again, the same process as before for continuous joints, to be able to do a continuous joint analysis combined with this different panel analysis. So that's all done there. So let's just look at our load extractions. If we have a 1D stiffener, so there's our skin loads. So let's just highlight that quickly. Go to Apex. So that's the elements that we consider to calculate our skin loads, skin applied loads. Let's look at our 1D stiffener. So there we extract our 1D stiffener elements. Calculation of the applied load there. So let's quickly have a look at how we do what we do with 2Ds when the stiffener is meshed in 2D. So if you remember there, we've got meshed modeled these 2 dummy beam spans. So that's the skin loads that we use there. And again, we ignore the glue joint if there's a glue joint applicable to that analysis. So look how we extract our stiffener data. So that's for the one cross section associated with that dummy beam span. We extract those elements to calculate the applied loads, and then we do the same on the opposite side. Use those elements. So in actual fact, what you do is we're actually doing 2 calculations, assuming the length is associated with the full length of the one cross section and the full length of the other cross section. So we sort of like cater for both conditions there, the analysis. Right. So let's have a look at our stuff panel analysis and working with native BDFs. So Apex is very nice. It's very efficient, and you want to use DFC, but I think now I need to rebuild all my models in Apex, and that is actually not required because DFC can work with native BDFs. So it can work with PDFs. All it needs is a PDF. You can create it in Patron and Answer, Hypermesh, etc. And we can use Apex and DFC then to analyze those BDFs with the full capability that's available in DFC. So for that, I'm going to do live demo quickly. Right, so DFC has got a BDF functionality where you select your BDF, you browse to it, and you can import your BDF. It then you can select how you want to organize your BDF. So it will then import the BDF into Apex. Then what we do then is we use Apex geometry and mesh functionality, and we create geometry on the mesh of that BDF. And the outcome of that is that we sit with state like this. So we have what we call a NURB surface. So that's the NURB geometry created by Apex. And this geometry is not associated with any of the elements. So it's just pure geometry, unassociated. Then we have faceted geometry. So this geometry is associated to the mesh, to the elements and so forth. Then we have our beam spans, and then we have our meshes. So again, what we can do is we can create dummy beam spans and apply our normal way of DFC working. We can apply joint allowables to it, and then which will then trigger a stiffened panel analysis. So what we do is we actually use the NURB data as tracing paper to identify analysis regions of where we want to analyze things according to the mesh policies that's available in DFC. So just to show the tracing paper philosophy, I'm just going to edge drag that. And I've picked the wrong one. Let me just undo this. Right, so let me just hide the facet geometry. Right, so now we only work with our NURB surface. Just to show the philosophy. So let me just drag that thing there. All right, so you can see that geometry is unassociated. So now we can just do the same process as before. We extract the edge on the NURB of the beam span, and we can extract the data for our stiffened panel analysis. And there we have our data. Come to DFC and we import that data into DFC, and now we have a stiffened panel analysis. I'll just have a look at what is extracted. So go to Apex. So then you'll see that we extract the data that are as close as possible to our tracing paper. So for the skin, we will then use those elements. For example, calculate the applied skin load. So this is just to demonstrate the tracing paper philosophy. But in the end of the day, we can use native BDF data, and using the NURB data as tracing paper, we can then utilize all the capability in DFC for automatic extraction and analysis of all the methods that's available in DFC. So this is just a very nice, a very cool feature of DFC. All right. Again, all our methods are available, documented for scrutiny. And again, if you don't agree, you can tailor it, or if you've got your own code, we can accommodate it. Okay, so that is different panels. And I think, Zak, now is a good time for questions.
Yep, we can do it. Sorry, there was one in the chat that I just need to verify, or clarify rather. Does it, and I assume this is related to the stiffened panel method. Does the tool work for element stresses and forces only? I assume that it depends on the method that's applicable that you want to analyze. That will dictate whether DFC will look at your elemental stresses or the associated forces.
Okay, so to answer that question, so you need to look at your method and what the method needs input. So the other method either needs loads or needs stresses or something. So then you decide how you want to import the loads so that you are able to calculate the data that you need for the method. So each of our methods has got a load extraction assigned to it. So you're able to get your loads to be able to calculate your RF for that method. Then I see here are units for methods in SI only. No, we do both SI and imperial units. So you can have go here. No, this one here. So we DFC support those units. So they are the common SI units and then the common imperial units as well. So we can do both SI and imperial units.
Israel, does that answer your question?
Just about the tool working with the element system forces only. My aim was to understand if the tool is using pattern free body load extraction tool. Does it have any use of the tool, the pattern free body load extraction function that is inside pattern? Do you use that with this tool?
The free body load extraction.
Yes.
No, I don't use that. I don't have
Okay.
the capability. I don't have the capability yet. But of course, if there is a requirement for it, then we can always address it.
And per the imperial and SI units, for example, for like you probably have a baseline of those units. So you are either working in SI, and if there's an imperial unit selection of any user, then you are converting all your units to SI after. Once their input is imperial, then you are converting it to SI, right? I mean, the tool is going in, like it has a baseline in one of those units, but then you are converting the other one. Which one is the baseline? That was my main question.
So the tool is dynamic, right? So at the moment, this thing is set for that SI units, but if you click that unit, then all data is converted automatically to imperial units. So it's dynamic. Okay. Then if you import data, so from Apex, it will then compare whether your data in Apex are imperial or metric, and it will just warn you, and it actually won't import the data if it's not in consistent units. If Apex and DFC is not consistent, then you either change one of the two and you import the data so that it's consistent, and then you can just chop and change as you like after that.
Okay, to expand on that, let's say you are looking at buckling on a panel.
Yes.
The panel has 4 edges simply supported, for example.
Yeah.
So
Yes.
we have the graph from Brun. Brun is imperial. The
Yes.
units from Brun are imperial. So if you were to perform all those analysis in SI, then do you use the Brun buckling curves? So they are imperial. And if someone's performing analysis in SI, do they change them to imperial and just like put them there? How does that go?
Okay, so the input to DFC can either be SI units or imperial units, right? The actual calculation is always done in SI units. So what I do is I do take all the Brun data, all the graphs, all of that is converted to SI data. So the input to the code is can be imperial or SI. The
Uh-huh.
code will then convert it to SI, do the calculation in SI, and then the output is whatever the input unit was, whether it's SI or imperial, it will then export it to the input unit.
Okay, that explains it. So you are using the buckling curves in SI, the buckling curves that are in SI units, not imperial. So you have all of the setup in SI units originally.
Correct. So I take any imperial data, I convert to SI, and that is then used in the code.
Okay, that explains. Thank you.
Okay.
Okay. While we wait, I think Marco, between the two methods, I saw you unmute yourself. Were there any questions from your side?
No. It was answered in the second one. Thanks.
Okay.
I have
One question.
Sorry.
Sorry, one question from my side. Up till limit load, this analysis is good because there's no plastic deformation. But if you go to ultimate loads, the fasteners can yield and redistribute. Do you have a post-buckling analysis for that or not?
No. So the the post-buckling loads are as per the method. If you've got a continuous joint, obviously there's no fasteners included in that. So it just takes the continuous joint data and the requirements as per the NACA methods. If you've got it modeled as discrete joints, the loads stay linear.
So if you got it modeled as discrete, you got to then redistribute the numbers when by yourself or whatever outside.
Correct.
Because at the end of the stringer, you'll get peaking loads that won't be correct.
Correct.
Okay. All right. Thanks.
Yeah. Israel?
Yeah. I know this is just like work in progress right now, but are you planning to send us like any kind of material regarding this tool? So maybe we communicate it to the customers and check it ourselves to see if it's viable for that kind of stuff. What's the plan on that side?
So if you want to know more, we can have a separate session and in detail discuss what you actually require from us and we can go from there. If so, Zak, I think we can set something up like that.
Yeah, sure. Israel, I think the easiest would be, look, as I tried to make these sessions as simple as possible, but it's also a bit dangerous to do it because there is quite a lot to it. I mean, we discussed only two methods here, and we all know that the aircraft has a lot more structural components than only fasteners and stiffened panels. The best would be to maybe look at the requirement from the typical or the specific application and maybe discuss the methods applicable to that and see how we can assist with that. I think ultimately to start off with is that we do on the one side the automatic calculation of all of the methods that's available within DFC to accelerate the stress analysis and design process, but we also do the fundamental education associated with each and every method that's associated to the structural design that's that's involved with any aerostructure. So yeah, I think the best is we tailor that to the specific application SREF and take it from there.
Okay, two follow-up questions. If a customer wanted to change the methodology that is used in the calculation, is it as easy as updating an Excel file calculation, or do you have to go into Python and just change the code from Python, just like the equation is there and you just change it, where does the actual, like the Excel calculation take place? In which code?
Okay, so the Excel that you see, that's just a user interface. No calculations are done in Excel. It's just a convenient way to use Excel and incorporate Excel with DFC, and you can do your own calculations as well in Excel. But the actual DFC calculations is not done in Excel, so that's all done by code. So if there are changes or tailoring required, then it requires an update of the Python code.
So is the code language, is that Python?
Yes. So the actual
Or
code is done in Python, yes.
you don't have like some shell coding that is like addressing to some C++, whatever. It is in Python. So if someone wants to change it, they go to Python code and change the code from that. Is it easy to update that? This would just be a command, I think, from your future customers, so they would want to update some of those methods that they see.
Yeah, so that is actually what I earmarked. I remember someone asked this, I think it was you that asked the same question last time. So I will for our next session, I will do an example of how it can be customized. But so the user does not have access to the actual Python code. So if Python code needs to be updated, then we must do the updating of the Python code. However, we do produce a file, a text file that's similar to a PDF file. It contains the input data for the methods. It's a text file. So if the user has got any other code that's C++ or Python or whatever, all he needs to do is read the file to get all the input data. He can run his own code to calculate the RFs, and he just writes the results back to that same file. And then, so DFC will provide the input. The user uses his code to create the output, populate the output data in the same file, and DFC will then just read the data from there again and populate the user interface with the results. So that's basically how customization can work as well.
You probably have a separate Python subroutine file for each one of the methods there, right?
Yes.
So if someone wants to update it, they just open that regarding that Python file, they just open that and go through all the calculations and just update calculations in the Python.
No, no. That's what I said. The Python code is my IP. I don't distribute the IP of the Python code. So the code is compiled code. So the user does not have access to the raw Python code. Because then I will kill my business if I do that.
No, I mean, they're pretty generic, the aerospace calculations. Like someone with 3, 4, 5 or 10 years experience, they set up their own methodologies or they inherit the company methodologies. So they are pretty much standard in the industry. So you want to have similar type of calculations that your previous engineers in the company had been using so far. So just to be able to follow that suit, they just need to be able to update that themselves. Otherwise, they may not be able to give that proprietary data, but those calculations to a third partner. To like, there could be a problem you could face with this tool. I think it should be customizable somehow, because the Python side, those calculations, the equations that are used, I think that's the backbone of how useful this tool would be for any customer that is planning to buy this.
Yeah.
Just brainstorming, really.
Yeah. We can discuss that. But like I said, if the user's got his own code, we can incorporate that. It's not a problem. Then if he run my code and runs his code and he doesn't get the same answer, then my code is just there as let's call it the starting point for discussion. If he doesn't like it, then he can use his own code. And use his own code with his own company proprietary information, etc., to do the calculations. And then DFC is there just for the automation and the ease of use and all of that. It comes with DFC. But Like I said, you can then use his own company methods for analysis.
Do you have a date for rollout? Like, are you gonna start spreading this around, advertising this to companies anytime soon? Like, is it at this maturity state where it can be rolled out to a customer, do you think?
It's been rolled out for 2 years already, so it's available now. So we already have customers using the software.
Are they big companies?
Well, it's South African companies, so I don't know what you mean by big or small.
I mean, let's say more than 3,000 people
No,
in it. Okay.
we don't have companies in South Africa with aviation that's more than 3,000.
I don't even think we have 3,000 engineers in South Africa.
Yeah.
No, I mean like a big aerospace company would have more than 3,000 people. That's why I was asking, like, are any other big aerospace companies using this or defense companies? Probably not at this stage, but could be possible, I guess, in the future.
Yeah, well, not in South Africa.
Okay. Thank you. That's all from me.
Okay.
So if there's not any other questions, our next session will be in September. If there's any suggestions or anything that you guys like us to go a bit deeper in on as well, you're welcome to send it to me. We will cover maybe more of the methods as well as a little bit of the customization as well, and also the tools that's available within MEC Apex with the help of DFC. If there's no other questions, I think we can end the session. Like I say, we will make the recording available if there's any of your colleagues that would like to see this. And yeah, we can take it from there. Israel, I'll be in touch with you guys as well. And yeah, thanks for everybody. Thanks for your time, and we'll be in touch soon.
Okay. Thanks, Jack, Zach,
Thank you.
and JJ. Cheers.
Okay, thank you, Marco. Thank you, guys.
Thanks.
Thank you. See you soon.
Yeah, Zach, I will then contact you that we can set up a separate session with SRF.
Yep.
To go a little bit more in detail. Okay.
Yep, we can do that. 100%.
Alright.
You could send an email. I'll respond to that. I think we just need to, like, internally within BIAS engineering team, we want to see which methods we can pick from there. So we need some homework to do on our side. So I think we could aim for around mid of August for that session. So we are more prepared and it could be more productive.
For sure. I think, yeah, Israel, we can go into the details of that. My personal experience, JJ can correct me if I'm wrong. I would suggest that if there is an example or a existing case that we can help that I can help to explain and clarify. But yeah, I think that will be the easiest.
Okay.
Okay.
We can discuss the details after this.
Offline, yes.
Cool.
Cool.
Thank you.
Thanks a lot, eh?
Okay. Thank you, guys.
Cool. Bye-bye.